Hello, everyone, and welcome to another Mini Sky Tonight. So I had a young viewer approach me and mention that I was remiss in my solar system tour. They told me that I forgot the most important celestial body in our solar system, the sun. They said without the sun, we wouldn't have a solar system. And they're right. But in my defense, when I was doing the solar system tour, I was just focusing on the planets, the system around the sun itself, the 8 planets that make up the solar system. So to help out this one student, I agree with them. Without the sun, we wouldn't have a solar system. So let's talk about the biggest and brightest star that is closest to our sun and some of the unique details that make our star amazing. So, the sun is named after the Roman god Sol, hence the term solar system, the system of Sol. So that's where we get the term solar, and why that term is often used is because it comes from the original name for the sun. In fact, sometimes when we say sun, it comes from the Old English word sonne, so hence sun. Now, obviously, every culture has observed the sun. Without the sun, we wouldn't have some of the amazing things we have on our planet. We wouldn't have light, heat, and energy to sustain our life-filled planet. So many cultures have worshipped the sun because they realize without the sun, we wouldn't have Earth. And they often would change their cultures and their religions, as well as some of even their architecture was shaped around the sun because of their dependency upon it. And the sun has gone by several different names: Apollo, Utu, Ra, Helios, and many more. In fact, many cultures realize that without the sun, we wouldn't have what we have today. So sometimes even during the winter time, they would host festivities to celebrate the sun. It was actually the Chinese astronomers in the ancient times that were studying the sun even more in a different way that they realized that there were sunspots on the sun. So they saw these unique features. But in their recordings, they thought they were just like clouds or wisps that would go across the sun, not necessarily a part of the sun. The Babylonians realized that the sun would be higher in certain times of the year and lower in certain times of the year. So they realized over the course of several months that the sun went through different motions. In fact, it was many cultures that also noticed this transition as well. And they thought, oh no, the sun is battling the powers of death and darkness, and we should encourage them, because without the sun, we lose life. So often around about the winter time, some of these festivities included lighting huge bonfires to encourage the sun to keep adding energy towards the sun to battle against darkness and death, and to be able to increase its altitude once again. So to them, it was a big deal, but now we understand that it's just the tilt of our Earth that gives the natural look of the rising and lowering of the sun over the course of the year. Okay, and I apologize if I butcher this gentleman's name. It's an ancient Greek name. Anaxagoras, I think is how you pronounce it, was the first to propose the sun was a ball in the sky. When he looked at the sun projected onto a sheet, he noticed a slight little smudge of the sunspot on the far right side. And he thought, it looks like the sunspot could keep going, as though if it was like a vase and the edge of the picture was on the other side. And you kind of can see it continuing. So he thought, well, maybe it's just like a vase that just needs to rotate. Maybe the sun just needs to turn. So he was the first to propose it was a ball in the sky. And of course, Galileo was the first to propose that sunspots were a part of the sun itself, rather than just these clouds that the ancient Chinese said that were just going in front of the sun. He noticed over the course of time, using a telescope and projecting the sun onto a wall, that those sunspots stayed in those positions over a course of period of time as the sun would change over the course of several days. So he noticed that those sunspots were a part of the sun. In fact, the image that you see right here is Galileo's drawing of some of those sunspots that he saw. Our sun is the biggest thing in our solar system. In fact, without our sun, we wouldn't have the rest of the planets because the mass of the sun is 99.86% of the entire mass of the solar system. So of all the planets combined, it only would equal 0.14% of the whole mass of the solar system. So our sun is a big deal. Without our sun having enough gravitational pull to put other planets into orbit, we wouldn't have a solar system. Our sun is an average G-class star. So what does that mean? It's on the Hertzsprung-Russell diagram where we categorize stars. And on the far left side is spectral classes of stars that are big, blue, and white, and we give them the designation O. And on the far right side are KM stars, which are your little dinky stars that are about ready to putter out. And they're kind of deep red in color. Where our sun is a G-class star, meaning it's right smack dab in the middle. If people are interested to learn about spectral classes of stars, leave it down in the comments below, and maybe for a future video topic, I'd be happy to cover over it. The surface temperature of the sun is roughly 9,000 degrees Fahrenheit, or close to 1,000,000 degrees Fahrenheit. So it's pretty hot. And given some of the coronal area, it's pretty hot as well. If I recall correctly, the corona, which is the atmosphere, is over 1,000,000 degrees Fahrenheit. But that's nothing compared to the core of the sun. The core temperature of the sun is over 27 million degrees Fahrenheit. It's incredibly hot. So we have all this heat and energy coming from the sun, but fortunately we are far enough away from it that the heat and light and energy that's coming from us from the sun is just right to where it can sustain our planet. So it's good to be around the sun, but not too close, but not too far away. Our sun is incredibly large for size. 1.3 million Earths could fit inside of it. So it's a pretty big star. In fact, if you were to take it in terms of mass, you would need about 333,000 Earths to equal the same mass as the sun. Crazy, right? Now, the power that I posted down there is the average power that is produced by the sun every second. So it's producing 3.83 times 10 to the 26 watts. What does that mean? That's basically 3,83 and 24 zeros. It's a very big number. So you think your little light bulbs in your house have a lot of power? That is nothing compared to the sun. In fact, for as far away as the sun is, by the time that the light does reach the sun, it does lose a little bit of power, but it's still roughly about 1,300 watts, give or take. So that's still pretty powerful. That's why we depend upon solar energy, because we're able to get that power from the sun. So let's take a look at the surface of the sun, which is known as the photosphere. And we'll go over in some of the different layers of the sun here in a minute. Once we take a picture of the surface of the sun up close and personal, unlike what you saw with Galileo's image, which he just saw this basically kind of orange, yellowish surface, up close and personal view is something completely different, because it's not a solid surface. Because even the ancient Chinese astronomers and even Galileo himself thought it was just a solid surface or a solid ball, but it's actually not solid at all. It's kind of composed of a material known as plasma and gas, heated at very high temperatures. And it's incredibly granulated. It kind of looks like bubbling soup if you see it over a course of time. And this surface, known as the photosphere, is roughly 300 miles thick. So it's not a good distance for the entirety of the sun, but it's still a good portion of the sun that we can see. And when light does leave the sun, it takes about 8 minutes to reach us from the surface of the sun. So this is kind of what the sun looks like up close and personal from a solar probe. So it kind of looks like this bubbly, churning, like boiling soup. Because as the material, as it reaches the surface and it cools off, it starts to sink down. Whereas in the material that is heated up is rising up and the dark material is going down. So it basically is kind of an inner exchange. So what you're seeing in that video is basically hot material rises and cool material sinks down, kind of creating this circulation. That circulation in the sun is what is known as the convection zone. So as hot material rises from the core, cooler material sinks down and gets reheated up, and so it cycles back and forth. So how is it the sun gets its energy? Many people speculated over a course of a long time it's the balls of fire. It's basically heating up. But in actuality, it's not fire at all. It has to deal with gravitational pressure and a process known as nuclear fusion. And in order to get nuclear fusion, we have to understand what is going on with the sun. Gravity pulls things towards the center. And while gravity pulls things towards the center, gas pushes back. Because when gas is put under pressure, it heats up. And so heat pushes out. So gravity and pressure are playing tug of war with one another. And the more layers of material you have to press, the more things get crowded. So think of it kind of like here with the acrobats, one on top of the other. The more acrobats you have on top, the more pressure it is for the guy on the bottom. And that's kind of what's going on in our sun. The upper atmosphere is not a lot of pressure, but as more material is being compressed due to gravity, the core, in the area close to the core, there's not a lot of room for particles to move around. So these particles can then ram together because there's just not enough space and they have to go somewhere because they have all this energy and they have to release it and there's nowhere to go. So they sometimes ram into each other. And that ramming is the process of nuclear fusion. So again, you have pressure pushing outward because the gas is heating up, and you have gravity pushing things in, so they're eventually reach an equilibrium. So in the core, where things are the most compressed, that is where you get the process of nuclear fusion, particles ramming together. Because at low speeds or very little energy, electromagnetic repulsion forces the electrons and particles to want to naturally push away from each other. But at high speeds and there's no place to go, there's strong enough force to bind them together because they ram into each other. And so this is where we get the process known as hydrogen fusion by proton-proton chain. So basically protons are ramming together because normally protons, two positive charges, don't like to attract one another. But if they have a lot of energy, like in the center of the core, and there's no room to go and they're being squeezed together, they will ram into each other. So let's do proton-proton chain. It's easy to do with your fingers. So you take your two fingers, you ram them together, you get a deuterium, proton, a neutron, and a neutrino. Now, from here, you're going to ram another proton into it. And you're going to get a helium-3 and a gamma ray. And now we're going to take two 3 heliums, ram them together, and you get 2 protons and a helium-4. So once again, 2 protons, deuterium and a neutrino, add another proton, you get a helium-3 plus a gamma ray, and 2 heliums rammed together, you get a heavy helium and 2 protons. So that is the process of proton-proton chain, to where you basically can take protons, ram them together to produce gamma rays, neutrinos, positrons, and heavier elements. And this can keep going on further and further down the chain to where you can get helium, carbon, nitrogen, oxygen, and so on. As more materials ram together, you get different elements. So how do we know that this process is going on in the sun? Because we can't just take it by face value of light. This is what is known as the Drunken photon walk, because a photon gets easily absorbed by particles, because to particles, photons can act as energy. So they take the photon, absorb it, and they get energy, and then they emit it out another direction. So hence the drunken walk. Basically, it gets absorbed, re-emitted, absorbed, re-emitted, absorbed, re-emitted, and it could take several thousands of years before one photon of light eventually escapes the sun. So we can't depend upon photons, the light and energy that we see from the sun, to say, oh, there's actually nuclear fusion going on. As we go back looking at here, so we can't look at gamma rays, positrons, or photons, for that matter, to tell us that there is indeed fusion going on in the sun. It's one particular particle that can tell us that there is fusion going on in the sun. And it's that little proton, that little particle known as a neutrino. That little particle doesn't interact with a lot of things. So hence why it just goes off on its own. It's neutral in charge and it doesn't interact with a lot of other things, so it can just go straight through. In fact, it can go straight through the sun. So neutrinos created during the fusion fly directly through the sun, and they can come towards Earth. And since it takes about 8 minutes for those neutrinos that leave the sun to hit Earth, we can detect them. So how do we detect them? Well, neutrinos, as I mentioned, since they don't interact with a lot of different things, we have to create special devices to be able to detect them. This is what is known as the Sudbury Neutrino Observatory. Basically, it's this big, huge tank of water, because neutrinos do indeed interact with water very well. And once the neutrino does enter the tank filled with water, we could detect the reaction of those neutrinos hitting the water, and hence why all this big, huge hexagonal sphere types of materials and wires and everything and detectors all looking in this little big bubble of water just to try to find those tiny little reactions. And the reason being why it's so down far underground is because we don't want any other sources interacting with the water. So we wanted to basically put it down underground to isolate it, to where if nothing's interacting with it during the day, no radiation from other sources on our planet, just the sun itself. And so that's how we're able to detect that there is indeed fusion going on in the sun right now, is we're detecting neutrinos coming from the sun, and that tells us indeed there is fusion going on in the sun. As I mentioned that there was a couple different layers of the sun, here is the entire structure and composition of our sun. So deep, deep, deep in the center, you have the core. That's the area that is completely compressed because of gravity. And in the core, that's where you get the energy generated from nuclear fusion. From there, outward, you get the radiative zone, where the energy that is created inside the sun is radiating outward. From there, it hits what is known as the convection zone, that underneath layer. And from there, you get the photosphere or the chromosphere. Basically, it's the physical surface of the sun that you see. And then after that, you have the atmosphere of the sun, which is known as the corona, which is basically an area of ionized elements and charged particles that escape the sun. So those are the different layers of the sun that we can see. And the majority of the sun is mostly hydrogen with a little bit of helium and other different types of elements, which we have detected using spectroscopy. So how is it we know all these different layers exist inside the sun? Well, we understand vibrations of the sun using different types of equipment. And we noticed that vibrations on the surface of the sun basically indicate that there's something else going on underneath. And those vibrations on the surface of the sun, kind of like how you can take something vibrating and be able to look at something like radar, that's kind of how we do it with the sun, where we look at the vibrations and realize there's something going underneath the surface, and those vibrations give us an indicator of what's going on inside. So by studying the sun in different light, we're able to see unique features of our sun. So what types of spacecraft have observed the sun, and how are we able to observe it? Well, the first series of spacecraft that indeed observed the sun was the Pioneer 6, 7, 8, and 9, and it was their job to understand the magnetic field and space weather. They understand that the sun would eject material and create weather that interacts with our planet. Next one is Helios 1 and 2, which studied solar wind and cosmic rays that come from the sun. And then ISEEE measured the energetic particles before it was sent over to a path of a comet. Basically, it was looking at all the energetic particles that were being ejected from the sun. And at that time, a comet was going by. And they're like, okay, we can't miss this opportunity. So they sent it into the path of the comet to basically do some readings of the comet itself before it couldn't project anymore. The Ulysses spacecraft, which is currently still in orbit around the sun, is basically studying the poles of the sun, because we're able to see the different surfaces of the sun facing us, but not particularly the poles. And then the Solar Maximum mission is basically studying solar flares. So it's their job to basically understand what solar flares and how powerful they are. And some of these spacecraft also that observe it, wind talks about solar wind. SDO basically was the one that gave us all the beautiful images that we see of our sun in ultraviolet light and in infrared, as well as the visible. SOHO was the one that basically helped us study, like the vibrations I showed you, was to help us understand the different layers of the sun using those vibrations. And of course, we have the Parco Solar Probe that basically is taking an up close and personal view of the corona and trying to understand why it's so hot. Even though it's the atmosphere of the sun, it's actually hotter than the physical surface. And several other spacecraft are basically doing different types of monitoring of the sun. And of course, we have some future missions that are coming up. The Solar Orbiter, which is basically going to understand the heliospheric physics of the sun, like how nuclear fusion works, as well as some of the processes that create the bubbling effect that you see, as well as understanding the sun's magnetic field and how we can detect possible future sunspots. And of course, ADIA is going to do further studies of the solar corona. So these are just some of the different spacecraft that are going to be studying our sun. And of course, obviously, you can observe the sun in many different ways. You don't have to necessarily wonder, okay, where is it going to be in the sky? It's up every day. So, but the question is how do you safely observe it? You simply just can't use solar glasses. That is completely different. You can't just use your sunglasses. Those help protect a little bit for your eyes, but not staring at the bright source. So you need to have protective gear. You can get some solar eclipse glasses, but they're not completely safe because the film inside of them, as powerful as it is, it's very flimsy and can easily break. So you have to take good care of them if you are indeed using them, and you can't stare at the sun for too long. But what I usually recommend for people, if they want to observe the sun safely, use a designated solar filter for a telescope. It's made of specific types of material that allows you to be able to polarize majority of the light from the sun and to be able to observe the sun safely. But even then, you can only observe the sun for so long before it starts heating up and or causing problems with your eyes. In short, play it safe. So that is our sun, the closest star to us. If you have any questions or comments, leave it down in the comments below. If there's a topic you would love for me to cover over, leave it down in the comments as well. And until next time, stay safe, stay healthy, and as always, never stop learning.